The first tool that we'll need to cover when we want to deep learning is linear algebra. Well, the reason is very simple, because a lot of the tools that are required in deep learning are large amounts of computations. And linear algebra is just really good at representing those. It's also really good at representing many of the functions that we'll work with. So we need to get started. Now, this obviously is no substitute for a proper linear algebra class. But we'll try to cover all the basic things that you'll need at least to get started, and the rest we'll probably cover in learning by doing. So let's start with something very simple. First thing are scalars. So scalars is something that we all know. You can do simple things with them. You can add them. You can multiply them. You can compute functions like sine or cosine of them. And you can do things like, well, what's the length of A? Well, it's A if A is greater than 0 and minus A otherwise, so it's just the absolute value. This does a couple of nice things. It satisfies the triangle inequality. So A plus B is less equal than A, the length of A plus the length of B. And the absolute value of A times B is the absolute value of A times the absolute value of B. No particular surprises here. Now let's look at vectors. Again, I can do very simple things. I can add them. So C is A plus B. And in this case, I have Ci is AI plus Bi. I can also multiply alpha and B. And now in this case, so you already noticed it's not I'm multiplying A and B. What I'm doing is I'm basically coordinate-wise multiplying the Bi's with some coefficient alpha in order to get Ci. I can also do things like the sine of A, and in this case I'm just applying it element-wise. Now, the interesting thing is when it comes to measuring the length, well, I have a little bit of freedom, but the most common thing that we would do is we would probably define the length of a vector A to be just the Euclidean length of that, right? So the sum over I going from 1 to m, AI squared, and then the square root. I mean, for 2 dimensions, that's the Pythagoras theorem. And in general, well, that's just how you define the length, right? Now, a really useful thing of lengths, or norms as mathematicians call them, is the norm of A is greater or equal than 0 for all A, and that the norm of A plus B is less equal than the norm of A plus the norm of B. So this is just our triangle inequality again. And furthermore, if I scale A with B, then I get, absolute value of A times the length of B. Why the absolute value of A? Well, because otherwise I could get something negative. Now, the norm that we just looked at isn't the only one. There are lots of others. For instance, imagine that you're in Manhattan and you want to go from maybe 2nd Avenue, 5th Street to maybe 4th Avenue, 10th Street. Well, you would basically have to traverse the avenues and you would have to traverse the streets. And you can't really walk diagonally unless there's some derelict block and you go across a construction site. But in general, you basically go either east-west or north-south. And so therefore, the distance is really the distance in streets plus the distance in avenues, which is why a distance that's defined this way is sometimes also called the Manhattan distance. To make a long story short, it's basically the sum over the absolute values of the coefficient-wise distances. In other words, also the L1 distance. Now, if you look at it in pictures, well, vector addition, let's say we add the blue and the orange vector, well, in that case, we get the green vector. All you do is you take one vector, you piece it together with the other vector, and then you get the diagonal vector that combines them. Likewise, scaling vectors is easy, so I can, for instance, have C equals alpha times B, and all I'm doing is I'm taking the original vector and just making it longer. Now, why do mathematicians like this? Because it's essentially their version of writing a parallel for all do. Now the latter is, by the way, also music to our ears, because this is exactly what GPUs are really good at, where it's also easy to write code. So this is sometimes called a trivial way of parallelizing things. And we all like it when it's easy for our GPUs to do work nicely in parallel, which is why people like to write things down in vectors, or as we'll soon see, also matrices. A rather important property is the dot product. So the dot product is the sum of the coefficient-wise products. So in other words, A transpose B is the sum over I of AI BI. Now we call two vectors orthogonal if A transpose B equals 0. So you might ask, well, is that something special? Yes, actually, it turns out that if we have two vectors that are orthogonal to a third one, then their linear combination is also orthogonal. So let's actually quickly prove this on the whiteboard. If we have vectors, let's say A, B, where both are A transpose C equals 0 and B transpose C equals 0, then of course alpha times A plus beta times B transpose C, well, that's nothing else than alpha times A transpose C plus beta times B transpose C. And we'll already know that this is 0, and that term is 0. So this is, of course, 0. So we've just proven that any linear combination of those two vectors also has to be orthogonal to C. This type of linearity is something rather convenient that we'll be exploiting in the future. Now matrices do something very, very similar. I can, for instance, add them together. I can multiply them. It turns out matrices actually also form a vector space, so in that sense they're not that much different from what we had before. I can, adding them is just you add them coefficient-wise, and you can overall scale them. You can apply point-wise things like sine and cosine. But I will be able to do other things with them as well, namely I can multiply them, and this is where actually all the magic happens. Now, function analysis then takes this yet further by going from finite dimensional objects to infinite dimensional objects. So this is often a little bit more complex. For all intents and purposes here, essentially assume that wherever we have a vector, you can substitute that for a function. Wherever we had a matrix, you can substitute it for a linear operator. And most theorems sort of kind of work in the same way in infinite dimensional spaces, except that, yeah, you have sums over possibly infinite numbers of terms, and that adds a little bit of mathematical complexity. A lot of interesting things happen. You can prove lots of exciting new theorems, and the proofs get more complicated. But the intuition pretty much carries over. One word of caution: when we apply functions to matrices, we apply them coefficient-wise. In some cases, mathematicians may actually mean that we apply them to the matrices as entire arguments. So for instance, you could have something like a matrix exponential, so e to some matrix, and that's, of course, identity matrix plus, matrix plus matrix squared times 1/2 plus, 1/6 times the matrix 3 times, and so on. So just, as you would have in the Taylor expansion. We don't do that here. So assume the dumbest, plainest, simplest definition of what sine or cosine of a matrix is, unless we explicitly say so otherwise. Now, multiplications, you can do very simple things. For instance, you can multiply a matrix by a vector. And all it is, if you will, it's just taking inner products between the matrix, between the vector and the first row of the matrix, the vector and the second row of the matrix, and so on and so on. And so therefore, if I have a 3 by 4 matrix times a 4-dimensional vector, I get the 3-dimensional vector out of it. Right? In other words, C equals A times B. So in that case, I get, Ci equals, sum over J, Aij, Bj. Okay. What that means in practice is that those matrices effectively distort the space. They perform some shear transform on a bunch of vectors to get some new vectors out of it. Now, I can do those multiplications not just between matrices and vectors, but between pairs of matrices. For instance, if I don't just have a single vector, in the green case as before, but I have multiple of them, then I just stack up the results as they go. And with that, if I multiply a 3 by 4 matrix by a 4 by 5 matrix, then I get the 3 by 5 matrix out of it. And very unsurprisingly, I get that Cik is now the sum over J, Aij, Bjk. Norms are a rather useful thing to have in this case. And those norms are defined in such a way that the inequality holds. If I have C equals A times B, then the inequality has to hold that the norm of C has to be less equal the norm of A times the norm of B. And now, depending on how you define the norms on C and B, you get different definitions for the norm of A. And one of the more common ones is that if you assume that C and B satisfy the Euclidean norm, so basically L2 norm, then while the norm of A is what is sometimes also referred to as the largest eigenvalue of that matrix. Now, this really can lead you down a rabbit hole, and there's this beautiful area of function analysis and operator theory, and I would strongly encourage you to take a class on that if you're interested in these things. For the purpose here of this course, we'll only worry really about two things. One is the largest eigenvalue, and we'll get to that in a moment. The other one is just the sum over the squares of all the entries of the matrix. In other words, I'm treating the matrix like a vector by just taking the matrix, smashing it out to a long vector, and summing over all the terms. That's also called the Frobenius norm. Okay? Now, I briefly mentioned eigenvectors and eigenvalues. Well, eigenvectors are those vectors that aren't changed by the matrix. So what I get is that basically A times X is lambda times X. And of course, that doesn't hold in general, but for an eigenvector, all the matrix does is just makes it longer or shorter. It doesn't actually change its direction. Now, for symmetric matrices, I can always find a complete decomposition of the matrix. In general, that's not true. So there we go. Now, symmetric matrices and special matrices beyond that, well, let's just quickly look at what they look like. So on the left, I have some completely generic matrix. Matrix is symmetric if I have Aij equals Aji. In other words, if I flip the entries, I get the same thing. And the matrix in the middle actually does that. If you look at the colors and they represent the numerical entries, you can see that I could flip the matrix over on its main diagonal and I'd get the same matrix back. Now, if I have something antisymmetric, namely Aij is minus Aji, then, okay, I try to illustrate that by the matrix on the right. And since it's pretty hard to draw in pictures negative numbers or the opposite sign, I just switched the border colors and the hollow dark colors, so the white and blue and the blue and white parts are meant to be inverses of each other, or as in negatives. Now, a very obvious consequence of aij equals minus aji is that the diagonal of the antisymmetric matrix has to be all zeros, because in that case I have aii equals minus aii, and that can only be satisfied for zeros. The last thing in this context are positive definite matrices, and they generalize the notion of what it means to compute the length of a vector. Remember, the norm squared in the Euclidean sense of this x squared is x transpose x. So this generalizes to x transpose ax greater or equal than 0. So matrices A that satisfy this property for all x are positive semi-definite. Matrices that satisfy this property strictly for all non-zero vectors are positive definite. Now, a couple more things. So orthogonal matrices. So all the rows of a matrix are orthogonal to each other, and in this case, we refer to this matrix as an orthogonal matrix. So what that means is if I take an inner product between one row and another row, so uij and ukj, so these are different rows. If I sum over all the j, so that's like the dot product between those two rows, then I get delta ik. In other words, it's 0 if the rows don't match, and it's 1 if they do match. So I know that all the vectors have unit length. Unit length means length 1. And that also they are mutually orthogonal. Now, as a homework, you can show that if u transpose equals 1, then also u transpose u equals 1. Now, the latter is just writing out that formula in matrix form. Special matrices are permutations. So permutation matrices are the ones where Pij is 1 if and only j is given by a permutation of I. So pi is some permutation that I picked, and this permutation then defines a matrix. Now, why do we care about stuff like this in deep learning? For instance, if we have, an embedding of words or whatever, well, we might have some word ID, and then we get some mapping to, some dimension that we actually care about. Yeah, that's one of the reasons why we care. Also, a quick assignment for you. Try to prove that P is orthogonal. That this matrix Pij that I just defined, this permutation matrix, is an orthogonal matrix. Now, lastly, why do we really care about it? Okay, so this is a picture of NVIDIA's Turing GPU. And if you look at it, you see lots of repeated patterns. You see all those little cells. Those are essentially cores. And GPUs have many, many, many of them. And it just means that they can process many, many operations in parallel simultaneously. So NVIDIA GPUs have around 2,000 of them. AMD GPUs have some other number. And it's a little bit of an architectural choice of how many you pick and how powerful they are. But basically, suffice it to say, they can process many operations in parallel simultaneously, which allows you to do a lot of things like matrix vector multiplies efficiently.